Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. 252 million years ago, Earth experienced the most catastrophic extinction event in its history. The Permian-Triassic boundary marked what paleontologists call the Great Dying, an apocalyptic event that eliminated 96% of marine species and 70% of terrestrial vertebrates. Volcanic eruptions in what is now Siberia spewed massive quantities of lava, ash, and toxic gases into the atmosphere, fundamentally altering the planet's climate and ocean chemistry. Yet from this devastation emerged one of evolution's most remarkable success stories. The surviving species found themselves in a world stripped bare, with ecological niches suddenly vacant and evolutionary opportunities abundant. Among these survivors were small, unassuming reptiles called archosaurs, whose descendants would eventually rule the Earth for over 160 million years. The early Triassic period, spanning from 252 to 247 million years ago, represented a time of gradual recovery. Earth's ecosystems slowly rebuilt themselves as carbon dioxide levels remained elevated and global temperatures soared. Forests of seed ferns and early conifers began to repopulate the barren landscapes, while in the oceans, new forms of marine life gradually filled the empty ecological roles left by their extinct predecessors. During the Middle Triassic, from 247 to 237 million years ago, the pace of evolutionary innovation accelerated dramatically. Reptilian diversity exploded as different lineages experimented with new body plans and ecological strategies. Cynodonts, the mammal-like reptiles, developed increasingly sophisticated jaw mechanisms and may have begun developing the first primitive hair-like structures. Meanwhile, marine reptiles such as ichthyosaurs and plesiosaurs were perfecting their aquatic adaptations. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe, it's free, and it helps us grow this community together. The stage was being set for the late Triassic revolution. Climate patterns were stabilizing, vegetation was becoming more diverse and abundant, and the fundamental ecological framework that would support large terrestrial vertebrates was falling into place. Atmospheric oxygen levels, which had dropped precipitously during the Great Dying, were slowly recovering, allowing for the metabolic demands of increasingly large and active animals. Tectonic forces were also reshaping the planet. The supercontinent Pangaea was beginning to show signs of the rifting that would eventually tear it apart, creating new geographical barriers and opportunities for evolutionary divergence. Volcanic activity, while still significant, was becoming more localized rather than globally catastrophic. Perhaps most importantly, the archosaur lineage was undergoing crucial evolutionary developments. These early reptiles were developing more efficient locomotion, with some species beginning to adopt semi-upright postures that would later evolve into the fully erect stance characteristic of dinosaurs. Their respiratory systems were becoming more sophisticated, featuring the air sac systems that would later allow dinosaurs to maintain active metabolisms even at enormous body sizes. The fossil record from this period reveals a world in transition, where ancient forms were giving way to evolutionary innovations that would define the Mesozoic era. Small thecodonts were developing the hip structures that would distinguish dinosaurs from other reptile groups, while the first archosaurs were experimenting with the bipedal locomotion that would become a hallmark of many dinosaur lineages. As the Middle Triassic drew to a close, all the pieces were falling into place for one of evolution's most dramatic transformations. The late Triassic would witness the emergence of the first true dinosaurs, setting in motion an evolutionary dynasty that would dominate terrestrial ecosystems until the asteroid impact that ended the Cretaceous period 66 million years ago. The late Triassic period, spanning from 237 to 201 million years ago, unfolded on an Earth dramatically different from today. The supercontinent Pangaea dominated the planet's surface, stretching from pole to pole and creating a massive landmass surrounded by the global ocean Panthalassa. This continental configuration profoundly influenced climate patterns, creating conditions that would prove ideal for the emergence and rapid diversification of dinosaurs. Global temperatures during the late Triassic were significantly warmer than today, with no polar ice caps and tropical conditions extending to much higher latitudes. Average global temperatures reached approximately 25 degrees Celsius, compared to today's 14 degrees Celsius. This greenhouse climate resulted from elevated atmospheric carbon dioxide levels, estimated at 4 to 6 times current concentrations, creating a powerful greenhouse effect that trapped heat throughout the planet's atmosphere. The absence of polar ice meant that sea levels were substantially higher than today, flooding large portions of what would become modern continents. Shallow epicontinental seas covered much of central North America, parts of Europe, and significant areas of what is now China and Southeast Asia. These warm, shallow marine environments supported diverse ecosystems and created humid coastal plains that extended far inland. Pangaea's immense size created extreme continental climate patterns. The interior regions experienced severe aridity, with vast desert systems stretching across much of what would become the American Southwest, Central Europe, and Central Asia. These arid zones were punctuated by seasonal monsoons that brought intense rainfall during brief wet seasons, creating a boom-and-bust climate cycle that profoundly influenced terrestrial ecosystems. The Tethys Sea, a large embayment that penetrated Pangaea from the east, played a crucial role in moderating regional climates. This warm tropical sea extended from what is now the Mediterranean region deep into Central Asia, creating more humid conditions along its margins and supporting lush vegetation that provided food resources for herbivorous reptiles. Atmospheric oxygen levels during the late Triassic were approximately 15 to 18%, lower than today's 21%, but sufficient to support large, active animals. This reduced oxygen concentration may have influenced early dinosaur evolution, favoring respiratory systems with enhanced efficiency. The air sac systems that would later characterize theropod dinosaurs and eventually birds may have originated as adaptations to these oxygen-limited conditions. Seasonal patterns were extreme due to Pangaea's size and position. The massive continental interior experienced temperature swings of 40 to 50 degrees Celsius between summer and winter, while coastal regions enjoyed more moderate seasonal variations. These extreme seasonality patterns created selective pressures that favored animals capable of behavioral and physiological flexibility. Volcanic activity remained significant throughout the late Triassic, though not at the catastrophic levels seen during the Permian-Triassic extinction. The Central Atlantic magmatic province was beginning to form as the first signs of Pangaea's eventual breakup appeared. This volcanic activity contributed to atmospheric carbon dioxide levels and created localized environmental disturbances that may have accelerated evolutionary processes. Plant communities during this period were dominated by seed ferns, early conifers, and cycads. Ferns carpeted the forest floors, while the first flowering plants may have been beginning their evolutionary journey, though they would not become ecologically significant until the Cretaceous period. These plant communities created complex terrestrial ecosystems with multiple trophic levels, providing the ecological foundation necessary for large terrestrial vertebrates. The combination of warm temperatures, seasonal rainfall patterns, and diverse plant communities created ideal conditions for reptilian evolution and diversification. Ectothermic reptiles could maintain active lifestyles year-round in most regions, while the abundant plant resources supported the first large herbivorous dinosaurs. The geographical barriers created by mountain ranges and desert systems promoted evolutionary divergence, leading to the rapid diversification of early dinosaur lineages across different regions of Pangaea. This late Triassic world, with its extreme climates and vast continental landscapes, provided the perfect evolutionary laboratory for the emergence of Earth's most successful vertebrate dynasty. In the Badlands of northwestern Argentina, paleontologists have uncovered some of the most significant fossils in Earth's history. These discoveries from the Ishigualasto Formation dating to approximately 230 million years ago, represent our earliest glimpses of the dinosaur lineage. Among these ancient remains lies Eoraptor lunensis, whose name means dawn thief from the Valley of the Moon, a creature that embodies the transition from primitive archosaurs to true dinosaurs. Eoraptor measured just 1 meter in length and weighed approximately 10 kilograms, resembling a small agile predator with a long tail and grasping hands. Its skeletal anatomy reveals the fundamental characteristics that would define all future dinosaurs: a 3-fingered hand with sharp claws, a distinctive hip structure with a perforate acetabulum, and ankle joints that allowed for efficient bipedal locomotion. These features distinguished early dinosaurs from their archosaurian relatives and provided the anatomical foundation for their eventual dominance. The hip structure of early dinosaurs represents one of their most significant evolutionary innovations. Unlike other reptiles, dinosaurs possessed a perforate acetabulum, meaning the hip socket contained an opening rather than solid bone. This configuration allowed for more efficient leg movement and supported the development of erect rather than sprawling postures. The femur could insert deeper into the hip socket, providing greater stability and more efficient muscle leverage for locomotion. Herrerasaurus ishigualastensis, another crucial early dinosaur from the same Argentine formations, provides additional insights into dinosaur origins. Measuring up to 6 meters in length and weighing approximately 400 kilograms, Herrerasaurus was significantly larger than Eoraptor and demonstrated the rapid size increase that characterized early dinosaur evolution. Its powerful jaws contained sharp, recurved teeth, ideal for processing meat, while its robust limbs and large claws marked it as a formidable predator. The evolutionary relationships of these early dinosaurs have generated considerable scientific debate. Phylogenetic analyses, which use anatomical characteristics to reconstruct evolutionary relationships, suggest that Eoraptor may represent a very early dinosaur or possibly a dinosaur sister group. Its combination of primitive and derived features places it at a crucial position in the dinosaur family tree, representing either the earliest known dinosaur or the closest known relative to all dinosaurs. Staurikosaurus pricei, discovered in Brazil's Santa Maria Formation, provides another piece of the early dinosaur puzzle. This 2-meter-long predator possessed the characteristic dinosaurian hip structure and bipedal stance, but retained several primitive features that illuminate the transition from ancestral archosaurs to true dinosaurs. It's relatively simple. Tooth structure and limb proportions suggest a more generalized lifestyle than later, more specialized dinosaurian predators. These early dinosaurs inhabited a world dominated by other archosaurian reptiles, including etosaurs, phytosaurs, and various crocodilomorph lineages. Dinosaurs were initially minor components of late Triassic ecosystems, occupying small-bodied predatory niches, while larger pseudosuchian archosaurs filled the roles of apex predators and large herbivores. This ecological context helps explain why early dinosaurs remained relatively small and generalized in their adaptations. The respiratory systems of early dinosaurs may have provided crucial advantages over their contemporaries. Evidence from bone histology and comparative anatomy suggests that even the earliest dinosaurs possessed enhanced respiratory efficiency, possibly including primitive air sac systems similar to those found in modern birds. These adaptations would have allowed dinosaurs to maintain higher activity levels and potentially supported their eventual ecological expansion. The discovery of early dinosaur fossils continues to reshape our understanding of dinosaur origins. Recent finds from Poland, Tanzania, and India have extended the geographical distribution of early dinosaurs and revealed previously unknown aspects of their diversity. These discoveries demonstrate that dinosaurs achieved a global distribution relatively quickly after their initial emergence, suggesting rapid evolutionary success even in their earliest phases. The study of these pioneering dinosaurs reveals that their eventual dominance was not inevitable or immediate, but rather the result of a complex interplay between evolutionary innovation, environmental opportunity, and ecological competition that would unfold over millions of years. The evolutionary success of dinosaurs resulted from a suite of anatomical and physiological innovations that provided significant advantages over their reptilian contemporaries. These adaptations, many of which evolved during the late Triassic period, would eventually enable dinosaurs to dominate terrestrial ecosystems for over 160 million years and achieve unprecedented diversity in body size, ecological roles, and global distribution. The dinosaurian respiratory system represents perhaps their most significant evolutionary innovation. Unlike the simple lung ventilation found in most reptiles, dinosaurs developed a complex system of air sacs connected to their lungs, similar to the system found in modern birds. This unidirectional airflow system allowed for more efficient oxygen extraction, enabling dinosaurs to maintain higher metabolic rates and activity levels than their contemporaries. Evidence for this system comes from pneumatic foramina, small openings in dinosaur vertebrae, and ribs that housed air sacs. This respiratory innovation had profound implications for dinosaur physiology and ecology. Enhanced oxygen extraction supported increased metabolic rates, allowing dinosaurs to sustain prolonged periods of activity. This metabolic advantage was particularly important in the oxygen-depleted atmosphere of the late Triassic, where atmospheric oxygen levels were significantly lower than today. The ability to extract oxygen more efficiently from the available air provided dinosaurs with a crucial competitive edge. Locomotor innovations further enhanced dinosaur success. The evolution of a fully erect posture, where the limbs extended directly beneath the body rather than sprawling to the sides, revolutionized terrestrial locomotion. This postural change reduced the energetic costs of movement and enabled more efficient stride mechanics. The dinosaurian ankle joint, characterized by a simple hinge mechanism, eliminated the complex rotational movements required by sprawling reptiles and allowed for more efficient forward propulsion. Bipedalism, which evolved early in dinosaur history, provided additional advantages. Bipedal locomotion freed the forelimbs for other functions, including prey manipulation, defense, and eventually flight in bird lineage dinosaurs. The long tail of early dinosaurs served as a dynamic counterbalance, allowing for rapid changes in direction during pursuit of prey or escape from predators. This enhanced maneuverability was particularly important for small-bodied early dinosaurs competing with larger archosaurian predators. Dinosaur bone histology reveals evidence for rapid growth rates that exceeded those of contemporary reptiles. Microscopic examination of dinosaur bone tissue shows extensive vascularization and fiber bone structure characteristic of fast-growing animals. This rapid growth allowed dinosaurs to reach adult size more quickly than their competitors, reducing the vulnerable juvenile period and enabling faster generation turnover rates that accelerated evolutionary processes. The dinosaurian reproductive system incorporated several innovations that enhanced reproductive success. Evidence from fossilized eggs and nests suggests that dinosaurs developed sophisticated nesting behaviors, including nest site selection, egg arrangement, and parental care. Some species constructed elaborate nest structures and may have practiced temperature-controlled incubation through behavioral thermoregulation or metabolic heat production. Dental adaptations in early dinosaurs demonstrate remarkable evolutionary flexibility. While primitive dinosaurs possessed relatively simple pointed teeth suitable for processing animal proteins, the lineage quickly diversified to include forms with specialized dental batteries for processing plant material. This dietary diversification allowed dinosaurs to exploit a broader range of ecological niches and reduced competition among different species. Dinosaur integument, or skin covering, underwent significant evolutionary changes throughout their history. While early dinosaurs likely possessed typical reptilian scales, the lineage eventually evolved a variety of integumentary structures, including primitive feathers, quills, and complex display structures. These innovations served multiple functions, including thermoregulation, camouflage, species recognition, and ultimately, flight. The cardiovascular system of dinosaurs may have incorporated innovations that supported their active lifestyles. Some, Evidence suggests that dinosaurs evolved four-chambered hearts, similar to those found in birds and mammals, allowing for complete separation of oxygenated and deoxygenated blood. This cardiac innovation would have enhanced oxygen delivery to tissues and supported the high metabolic demands of active, warm-blooded physiology. These interconnected innovations created a positive feedback system where each adaptation enhanced the effectiveness of others. Enhanced respiratory efficiency supported higher metabolic rates, which enabled rapid growth and active lifestyles, which in turn favored improved locomotor efficiency and sophisticated behaviors. This integrated suite of adaptations positioned dinosaurs to exploit new ecological opportunities and eventually dominate Mesozoic terrestrial ecosystems. The late Triassic world teemed with remarkable biodiversity, featuring complex ecosystems that supported an extraordinary array of life forms. These ecosystems provided the ecological stage upon which early dinosaurs made their debut, competing and coexisting with a diverse assemblage of reptiles, early mammals, marine creatures, and plant communities that together created some of the most dynamic biological communities in Earth's history. Terrestrial plant communities during the late Triassic were dominated by gymnosperms, particularly conifers, seed ferns, and cycads. Vast forests of Araucarioxylon and other primitive conifers covered humid lowlands and river valleys, while seed ferns such as Dicroidium formed extensive understory communities. These plants created complex three-dimensional habitats with multiple ecological niches, from canopy-dwelling insects to ground-dwelling arthropods and vertebrates. Ferns carpeted forest floors, creating dense, humid microhabitats that supported diverse communities of small vertebrates and invertebrates. The absence of flowering plants meant that late Triassic ecosystems lacked many of the ecological relationships we associate with modern terrestrial communities. Without flowering plants and their co-evolved insect pollinators, food webs were structured differently, with decomposer communities playing more prominent roles in nutrient cycling. This created opportunities for vertebrate herbivores to access plant resources that would later become less available as flowering plants evolved more sophisticated chemical defenses. Marine ecosystems during the late Triassic exhibited remarkable diversity and complexity. The warm, shallow seas supported extensive reef systems built by scleractinian corals, which were undergoing their initial evolutionary radiation following the Permian-Triassic extinction. These reefs provided habitat for diverse communities of brachiopods, mollusks, echinoderms, and arthropods. Ammonoids, which had survived the end Permian extinction, diversified rapidly and became dominant marine predators with shells reaching over 2 meters in diameter. Marine reptiles achieved extraordinary diversity during this period. Ichthyosaurs evolved into highly specialized aquatic predators, with some species reaching lengths of over 20 meters. Their dolphin-like body forms and sophisticated sensory systems made them apex predators in open ocean environments. Plesiosaurs developed into two distinct ecological forms: long-necked species that fed on fish and cephalopods, and short-necked species that functioned as marine apex predators capable of taking large prey. Terrestrial reptilian diversity during the late Triassic was unprecedented. Etosaurs, heavily armored herbivorous archosaurs, filled ecological roles similar to modern large herbivorous mammals. Some species, such as Desmatosuchus, reached lengths of 6 meters and possessed extensive dorsal armor that provided protection from predators. Phytosaurs, crocodile-like semi-aquatic predators, dominated freshwater environments and achieved remarkable diversity in body size and ecological specialization. Pseudosuchian archosaurs, the group that includes modern crocodilians, were particularly diverse and successful during the late Triassic. Rauisuchids functioned as terrestrial apex predators, with species like Postosuchus reaching lengths of 7 meters and occupying ecological roles later filled by large theropod dinosaurs. These predators possessed powerful limbs, massive skulls, and sophisticated sensory systems that made them formidable hunters. Early mammals, represented by groups such as Morganucodontids and Harameids, were already present during the late Triassic. Though they remained small and ecologically marginal, these tiny creatures typically weighing less than 100 grams, occupied nocturnal insectivorous niches and possessed sophisticated sensory adaptations, including enhanced hearing and olfaction. Their presence demonstrates that major mammalian evolutionary innovations were occurring contemporaneously with early dinosaur evolution. Therapsids, the mammal-like reptiles that had survived the end Permian extinction, continued to occupy important ecological roles during the late Triassic. Cynodonts achieved considerable diversity, with some species developing increasingly mammalian characteristics, including complex jaw mechanics, possible hair-like integument, and sophisticated parental care behaviors. These animals served as ecological bridges between typical reptilian and mammalian adaptive zones. Freshwater ecosystems supported diverse communities of fish, amphibians, and reptiles. Large temnospondyle amphibians, some reaching lengths of 6 meters, functioned as apex predators in aquatic environments. These animals possessed massive skulls with numerous sharp teeth and may have employed sit-and-wait predatory strategies. Similar to modern crocodilians, insect communities during the late Triassic were undergoing significant evolutionary changes. The diversification of holometabolous insects, those with complete metamorphosis, was accelerating, creating new ecological relationships and food web structures. These insects served as crucial pollinators for gymnosperm plants and formed the foundation of many terrestrial food webs. Within this complex ecological tapestry, early dinosaurs occupied relatively modest roles as small to medium-sized predators and herbivores. Their initial success resulted not from ecological dominance, but from their ability to exploit available niches efficiently while possessing evolutionary innovations that would later enable dramatic ecological expansion. The late Triassic ecosystem provided the perfect evolutionary laboratory for testing the anatomical and physiological innovations that would eventually propel dinosaurs to global dominance. 201 million years ago, Earth experienced another mass extinction event that would fundamentally reshape the trajectory of life on our planet. The Triassic-Jurassic extinction event, while less severe than the Great Dying that ended. The Permian eliminated approximately 76% of all species and created ecological opportunities that would allow dinosaurs to transition from minor ecosystem components to dominant terrestrial vertebrates. The primary cause of this extinction event was massive volcanic activity associated with the Central Atlantic Magmatic Province, one of the largest volcanic events in Earth's history. This enormous eruption occurred as the supercontinent Pangaea began splitting apart, creating the Atlantic Ocean basin. Volcanic activity extended across 4 million square kilometers, spanning what would become eastern North America, western Africa, southwestern Europe, and South America. The eruptions released an estimated 4 million cubic kilometers of lava over approximately 600,000 years. These eruptions had catastrophic environmental consequences. Massive quantities of carbon dioxide entered the atmosphere, creating intense greenhouse warming. Global temperatures rose by 3 to 4 degrees Celsius, while atmospheric carbon dioxide levels increased to 8 times pre-industrial concentrations. The volcanic emissions also included sulfur compounds that created acid rain and hydrogen sulfide that poisoned both terrestrial and marine environments. Ocean chemistry underwent dramatic changes during this period. Increased atmospheric carbon dioxide dissolved into seawater, creating severe ocean acidification that devastated marine ecosystems dependent on calcium carbonate. Coral reefs collapsed, and many groups of marine invertebrates experienced severe population crashes. The disruption of marine food webs had cascading effects that extended to terrestrial ecosystems dependent on marine-derived nutrients. Climate instability characterized the extinction period. The massive volcanic emissions created rapid climate fluctuations between extreme greenhouse warming and temporary cooling caused by volcanic ash and sulfur aerosols blocking sunlight. These rapid climate changes exceeded the adaptive capabilities of many species, particularly those with narrow environmental tolerances or limited dispersal abilities. Terrestrial plant communities suffered severe disruption. Pollen records show dramatic decreases in plant diversity and abundance, with some regions experiencing near-complete deforestation. The collapse of plant communities eliminated food resources for herbivorous animals and disrupted the foundation of terrestrial food webs. Seed fern communities, which had dominated many ecosystems throughout the Triassic, virtually disappeared, while conifer forests experienced severe population reductions. The extinction event particularly impacted large-bodied terrestrial vertebrates. Dinosaurs, the heavily armored herbivorous archosaurs that had been dominant herbivores throughout the late Triassic, completely disappeared. These animals, some reaching lengths of 6 meters, had been crucial components of terrestrial ecosystems, and their extinction created enormous ecological vacancies in herbivorous niches. Phytosaurs, the crocodile-like semi-aquatic predators that had dominated freshwater environments, also vanished entirely. These successful reptiles had achieved remarkable diversity during the late Triassic, with species adapted to various aquatic and semi-aquatic lifestyles. Their extinction eliminated major predatory pressure from freshwater and coastal environments. Many groups of pseudo-Suchian archosaurs, including the terrestrial apex predators known as Rauisuchids, suffered extinction. Rauisuchids such as Postosuchus had been the dominant large predators in late Triassic ecosystems, occupying ecological roles similar to those later filled by large theropod dinosaurs. Their disappearance removed major predatory pressure from terrestrial ecosystems and created opportunities for dinosaurian predators to expand into larger body size classes. Therapsids, the mammal-like reptiles that had survived the end Permian extinction and achieved considerable diversity during the Triassic, suffered severe losses. Many cynodont lineages vanished, though some survived to give rise to true mammals. The reduction in therapsid diversity eliminated competition for small-bodied ecological niches and may have facilitated early mammalian diversification. Marine reptiles experienced variable extinction patterns. Some ichthyosaur lineages disappeared, while others survived and diversified during the Jurassic period. Plesiosaurs were less severely affected and continued their evolutionary radiation. These differential survival patterns created new ecological structures in marine environments. Dinosaurs demonstrated remarkable resilience during this extinction event. While some early dinosaur lineages may have disappeared, the major dinosaurian groups not only survived, but began expanding rapidly in the aftermath. Theropod dinosaurs diversified into larger body sizes, filling predatory niches vacated by pseudo-Suchian archosaurs. Sauropodomorph dinosaurs expanded into large herbivorous roles previously occupied by aetosaurs and other archosaurian herbivores. The survival and subsequent success of dinosaurs during and after the Triassic-Jurassic extinction event demonstrates the effectiveness of their evolutionary innovations. Their efficient respiratory systems, advanced locomotory capabilities, and rapid growth rates provided crucial advantages during environmental stress. The elimination of major competitors and the availability of vacant ecological niches created unprecedented opportunities for dinosaurian evolutionary radiation. This extinction event marked the end of the Triassic world and set the stage for the Jurassic period, when dinosaurs would achieve the ecological dominance that would characterize the remainder of the Mesozoic era. The aftermath of the Triassic-Jurassic extinction event marked a pivotal moment in Earth's evolutionary history. As ecosystems recovered from the catastrophic volcanic disruptions, dinosaurs emerged from their relatively modest late Triassic, beginnings to establish the ecological dominance that would define the Mesozoic era. The evolutionary innovations developed during the late Triassic provided the foundation for one of the most successful vertebrate radiations in Earth's history. The early Jurassic period, beginning 201 million years ago, witnessed explosive dinosaurian diversification. Theropod dinosaurs rapidly expanded into larger body sizes, filling predatory niches vacated by extinct pseudo-Suchian archosaurs. Dilophosaurus, reaching lengths of 7 meters, exemplified this size increase, possessing the advanced respiratory systems and efficient locomotion inherited from late Triassic ancestors. These respiratory innovations, initially developed in small-bodied forms like Eoraptor, now supported active lifestyles in much larger predators. Sauropodomorph dinosaurs underwent perhaps the most dramatic evolutionary expansion. Early forms like Plateosaurus, already present in the late Triassic, gave rise to the massive sauropods that would become iconic symbols of the Jurassic period. Species such as Camarasaurus and Brontosaurus achieved body masses exceeding 30 tons, representing size increases of 3 orders of magnitude from their late Triassic ancestors. The air-sac respiratory systems developed during the late Triassic proved crucial for supporting the metabolic demands of these gigantic herbivores. The ecological vacuum left by extinct pterosaurs created unprecedented opportunities for herbivorous dinosaurs. Sauropods developed sophisticated feeding strategies, including high browsing that allowed them to access plant resources unavailable to other herbivores. Their long necks, supported by pneumatic vertebrae that reduced weight while maintaining strength, enabled them to exploit 3-dimensional feeding spaces with remarkable efficiency. This feeding innovation allowed single sauropod species to consume plant material equivalent to entire communities of smaller herbivores. Ornithischian dinosaurs, represented in the late Triassic by small forms like Pisanosaurus, diversified into numerous ecological roles during the Jurassic. Stegosaurs developed elaborate defensive armor and sophisticated feeding mechanisms for processing low-growing vegetation. Their success demonstrated how the basic dinosaurian body plan could be modified for specialized ecological roles while maintaining the fundamental advantages of erect posture and efficient locomotion. The elimination of phytosaurs created opportunities for dinosaurs to colonize semi-aquatic environments. Spinosaurid theropods, though not appearing until the Cretaceous, represented the culmination of dinosaurian adaptation to aquatic lifestyles. Their elongated skulls and specialized teeth for catching fish showed how dinosaurian innovations could be adapted for diverse ecological roles, including those previously dominated by other archosaurian groups. Respiratory system evolution continued throughout the Jurassic and Cretaceous periods, ultimately leading to the evolution of flight in the dinosaurian lineage that gave rise to birds. The air-sac systems first developed in late Triassic dinosaurs provided the physiological foundation for powered flight, enabling the evolution of Archaeopteryx and subsequent avian diversity. This respiratory innovation, initially developed for terrestrial locomotion, proved pre-adaptive for aerial locomotion. The rapid growth rates characteristic of dinosaurs, first evidenced in late Triassic forms, enabled accelerated evolutionary processes throughout the Mesozoic. Fast generation turnover allowed dinosaur populations to respond quickly to environmental changes and evolutionary pressures. This growth strategy proved particularly advantageous during periods of environmental instability and enabled dinosaurs to recover rapidly from localized extinctions. Dinosaurian reproductive strategies evolved increasing sophistication throughout the Mesozoic, building upon behaviors first developed in late Triassic ancestors. Evidence from fossilized nests and eggs reveals complex brooding behaviors, colonial, nesting and parental care that enhanced offspring survival. These reproductive innovations contributed to dinosaurian ecological success by reducing juvenile mortality and enabling population growth in competitive environments. The global distribution achieved by dinosaurs during the Mesozoic built upon the widespread geographic presence established during the late Triassic. Early dinosaurs had achieved nearly global distribution before the Triassic-Jurassic extinction, providing a foundation for subsequent colonization of new environments as Pangaea fragmented. Dinosaurs successfully adapted to the changing paleogeography of the Mesozoic, colonizing newly formed continents and island systems. The evolutionary success of dinosaurs throughout the Mesozoic era ultimately stemmed from the suite of innovations developed during their late Triassic origins. Enhanced respiratory efficiency, improved locomotory mechanics, rapid growth rates, and behavioral sophistication provided the foundation for ecological dominance that persisted for over 160 million years. Even today, dinosaurs continue their evolutionary success story through their avian descendants, which represent the most diverse vertebrate group on Earth. The late Triassic emergence of dinosaurs thus represents more than just the origin of a successful vertebrate. group. It marks the beginning of an evolutionary experiment that fundamentally changed the structure and function of terrestrial ecosystems. The innovations developed during this crucial period continue to influence modern ecosystems through the remarkable diversity and ecological importance of contemporary birds, the living legacy of the dinosaurian revolution that began in the shadow of the Triassic world.